Welcome back to the video on continuity. So in the previous videos we were talking about the limits of a function and what a function is. So this video is actually now talking about a continuity at a point x, which is equal to a. So a function f of x is continuous at a point x, which is equal to a, if the first point is if f at a exists. What does that mean? It means that f of a would be assuming a finite value. So it will be assuming a finite value, right? Then the second point is the limit as x approaches a of f of x exists as well. So existence of this limit only happens if and only if the limit as x approaches a from the negative of f of x is equal to the limit as x approaches a from the positive of f of x. Right, that's the existence of that limit. And the third point now is the limit as x approaches a of f of x should be equal to f of a. Those are the 3 points which guides us on continuity. So if any one of these points fails to hold, we cannot guarantee continuity. If any one of these points fails to hold, we cannot guarantee continuity. So you might see that on some examples, number 1 might hold as well as number 2, but number 3 might fail. We'll consider all those examples below. So as an example, we have f of x is equal to x squared is continuous at x is equal to 1. We want to test whether it is continuous. Since we know that we have 3 points which we should test. So for part 1, we are going to say f of 1 is equal to 1 squared plus 1, which is equal to 2. Therefore, f of 1 is defined. I'm just writing everything for clarity reasons. Right, f of 1 is defined. Then, the second stage is to prove whether the limit exists at f is equal to 1. So the limit as x approaches 1 of f of x is equal to the limit as x approaches 1 of x squared plus 1, which is equal to just 1 squared plus 1, which is equal to 2. And it's actually evident if you want to prove 3 now, we are actually seeing that limit as x approaches 1 of f of x squared plus 1 is actually equal to 2, which is equal to f of 1. Therefore, you can actually see that for this one, the first condition is here, the second condition is here, and the third condition is there. So the function f of x, which is equal to x squared plus 1, is continuous at x is equal to 1. So here you say, therefore, x squared plus 1 is continuous at x is equal to 1. That is the conclusion we get there. Right, let's now move to the next example, which is modulus of x over x. We want to determine whether modulus of x over x is continuous at x is equal to 0. Okay, so for this one now, we generally know that the graph for modulus of x over x should look like this. The graph for modulus of x should look like this. So we know that for values which are less than this one is minus 1, yes, and then 1. So this one is 1 and minus 1. So for x which is less than minus 1, we have which is less than 0, we have the graph as here, like the graph, our graph is there on this line, right? Then when we get to 0, so meaning that our graph is on this line, yeah? So when we get to 0, our graph skips to minus 1. That is our graph. So we can actually see that for this one, f of 0 is actually not defined. So for the first point, for this one, f of 0 is not defined. So for modulus of x over x is equal to f of x, f of 0 is suppose is not defined. Right. Therefore, modulus of x over x is not continuous at x is equal to 0. Right. Because you can actually see it's clear that if you try to put 0 there, down there, it will just give us infinity. So modulus of x over x is not defined at x is equal to 0. Then let's consider the second part for comparison's sake. Since you can actually see this one just failed immediately on the first one. What if we define this function at x is equal to 0? What will happen? That is the example which is coming next, which is f of x is equal to modulus of x over x, modulus of x over x and 0 if x is equal to 0. So let's consider that. Okay, for this case, unlike in the previous case where we just had modulus of x over x defining the entire function, we now have modulus of x over x and 0 if x is equal to 0 and if x is not equal to 0. That is what we now have. So what does this mean? It means that we now have our f of 0 defined. So the question should read is determine whether f of x, which is equal to that, is continuous at x is equal to 0. So the first point which we have to prove is the first point is we have to prove that f of a exists. So you can actually see that here f of 0 is equal to 0. Therefore, f of 0 is defined. Right? So that is the first point. Then part B is we want to prove that the limit, let me just refer back again. We have the limit should exist at this one. The limit is as x approaches a of f of x should exist. So limit is x approaches 0 of modulus of x over x should exist, right? It's such that. So here we are gonna prove it. So you're gonna say this is such that. So you're gonna consider the left and right limit. Limit as x approaches 0 from the negative of modulus of x over x, and which is we're going to consider the limit as x approaches 0 from the positive of modulus of x over x. So for the first case, this is simply equal to the limit as x approaches 0 from the negative of x over x minus x over x. Since we know that from the definition of the modulus, if we are actually in the negative side of 0, it should assume, like here, the definition of the modulus of x over x, if we are approaching 0 from this side, it's not like we are putting a negative value. We are approaching 0 from the negative. So 0 from the negative, and approaching 0 from the positive means this. 0 from the positive. So you can actually see our function is on this value. So it's actually on 1, and same applies here. Our function would be on -1 for values of x which are less than what? Which are less than 0. So what it means is this one is actually equal to limit as x approaches 0 from the positive of modulus of x over x, which is equal to the limit as x approaches 0 from the negative of -1, which is just equal to -1. And same applies this one. This one is limit as x approaches 0 from the positive of 1, which is just equal to 1. Right, so you can actually see that it's evident that the left and right limits are not equal. Okay, so since limit as x approaches 0 of modulus of x over x does not exist, because limit as x approaches 0 from the positive of f of modulus of x over x is not equal to the limit as x approaches 0 from the negative of modulus of x over x. Hence, the limit does not exist there. So it means that as a result, modulus f of x, which is equal to modulus of x over x 0, x not equal to 0, x equal to 0, is not continuous at x equals to 0. So that one means that it's not continuous at x equals to 0. That is what it means. Okay, to consider another example, there's this example which is in our document, determine whether the function defined by that is continuous at a point x is equal to 2. So we just use the same approach. So it's best for us to first sketch, though, like when a question asks you, a sketch will just help you to see what is happening, but sometimes it's not necessary, especially when you're in an exam situation. Sometimes time would be uh, very important to keep. So you need to make sure that you spend less time on each question. Okay, so here I'm just gonna first start by sketching how it looks like. This is a piecewise defined function. So the first part, we're gonna split our graph into three. Let's split it into three. So the first part is for x less than 2. So let's put our 2 here. Two there. Okay, just allow me to do this. I'm gonna put a 2 here. Then we have x equal to 2, and for x greater than 2, and for x less than 2. Okay, fine. So for x less than 2, we know that our graph is supposed to be x squared. Generally, the graph of x squared is like this. So in this case, we are going to consider it like this, from the negative going forward up to 2. Like that. Though it should pass through 0 there. So let me just restart it. So from the negative, passing through 0, going forward up to 2. Like that. That is how our graphs look like. So this is the graph for y is equal to x squared. But then, like, this graph doesn't touch 2. So I'm going to put a sign which shows that it doesn't touch 2 for x squared. That's why we have a strict less than, right? Then the graph for when x is equal to 2, we have when x is equal to 2, we have our graph being equal to 5. F of x is equal to 5. So y is equal to 5. I'm going to consider it. Just going to put it here. That's where y is equal to 5 is. So I'm just going to put a dot there, since you can actually see that that one is just a dot. Right? That's for 5. For uniformity, let me just let me just maintain the red color. So that's for this other graph, the f of x is equal to 5. Then the one for minus x plus 6. This one, we know that it's a straight line which intersects the y-axis at 6. So 6 should be up here. And also, it has got a negative gradient. And if we put our y equals to 0, we get x is equal to 6. So the graph should pass through here. So this one is 6. So we know that it is intersect point 6 and 6 somewhere there. But we want to see what does it assume at x is equal to 2. So if we were to substitute 2 in this, we're going to get minus 2 plus 6, which is going to give us minus 2 plus 6 is 4. So we are actually seeing that is equal to 4, which is similar to that one. So we'll be having that. Okay, that's how it looks like. So let me just shift my 6. Let me just say, it's just, let's just pretend there is 6 here. 6 is there. Right, so that is how our graph looks like. So we want to test whether the function is continuous at x is equal to 2. We are going to just use what we have, what we were doing before. We're going to test the 3 conditions. So the first condition to test, we ask ourselves, is f of 2 defined? Does it have a finite value at f at 2? So you can actually see that f at 2 is equal to 5. So in this case, our answer is, this one was the question. So our answer, f of 2 is equal to 5. Therefore, defined. Right? Then the next question we ask ourselves is number 2. Number 2, we ask ourselves whether the limit as x approaches 2 of f of x is defined. Does that limit exist? So for us to test whether that limit exists, we have to test using the 2 conditions, the left and right limits. Limit as x approaches 2 from the positive of f of x, and limit as x approaches 2 from the negative of f of x. But what do we know now? What do we know? And I would like to clarify on this statement. X approaching 2 from the negative doesn't mean that we are saying we substitute plus 2 or what. Or this one, x approaching 2 from the negative doesn't mean that we are substituting minus 2, right? It's just the approach we are following. We are coming from this side, approaching 2 from the negative. So you can actually see our function is assuming this x squared function from the negative. As it approaches 2 from the negative, it's actually on x squared graph. So here, this one is just equal to x squared. And as we, this one is for 2 from the negative. X squared is for 2 from the negative, and 2 from the positive. Now we are coming from this line here, so which is from the positive. Let me just put some little arrows for clarity's sake. Oh, let me replace this one. Okay, let me just put some arrows. So here we are approaching 2 from the positive. Here we are approaching 2 from the negative, right? And there is at x is equal to 2. You get it? So that's thing. So like whenever you are approaching 2 from the negative, we take that function, which f of x will be assuming in that direction. So here we have 2 from the negative, 2 from the positive. 2 from the positive, it will be assuming minus x plus 6. Right? Then this one is, we are just substituting 2. So whether we are approaching 2 from the negative, 2 from the positive. So these ones, 2 from the negative and 2 from the positive, is just making us point the function which our f would be equal to in that range. Not that it is just making us point the function which f of x will be assuming in that range. So what we just do here is we now substitute 2 in this function. If we substitute 2, we just get minus 2 plus 6. And here we get 2 squared, which is equal to 4. And minus 2 plus 6 is equal to 4. Therefore, since the left and right limits exist, since the left and right limits exist, this and are equal, this implies that the limit as x approaches 2 exists of f of x exists, and it's equal to 4. Right. Then number 3. So this one actually agreed with the first one and the second one. Is it gonna agree on the third one? So the third one is saying, if the limit exists and if f of 2 is defined, is f of 2 equal to the limit? So in this case, we know that our f of 2, we said from the definition, is equal to 5. And the limit from this second part, the limit we said is equal to 4 because the left and right limits are equal and are equal to 4. We have the limit. Okay, let's just say limit as x approaches 2 of f of x, which is equal to 4. So you can see that from the first one, we've managed to find that f of 2 is defined and is equal to 5. But from the second part, we managed to find that the limit of f of x as x approaches 2 is equal to 4. So it means that this one it's actually failing to hold on the last part. Therefore, f of x, which is equal to x squared 5 and minus x plus 6 is not continuous at x is equal to 2. Full stop. I'm just going to consider one example from the tutorial, then we move forward to the next topic. So for this example, we are given that the function f which maps r to r is defined by f of x is x squared minus 4 to x plus b and e to the x, is continuous at all points in r. Find the values of a and b. So for this one, we are actually given that the function is continuous at all points in R. It's continuous at all points in R. So which means that there are no gaps on this function. What does this mean? It means that, so let's just write the solution here. So since f of x is continuous at all points in R, it means that those three conditions hold. So we have f of a defined at all points, which is our f of x is defined at all points in R. And also the limit exists at all points in R. And also we actually talked about those 3 points. So we said f of a should be defined, the limit should exist, and the limit should be equal to f of a. Those are the 3 points. So that is what we know right now, that everything is holding. So we want to take advantage of that. Since f of x is continuous at all points in R, the limit as x approaches 2 from the positive of f of x. So we before maybe I do that, let's just sketch something which makes it visible. I'm not going to sketch the entire graph, but I'm just going to sketch something which we can use. So we have 2 here, and we have 0, and sorry, just confusing, 2 here, and we have 0. Why am I starting with 2? Let's have 2 here. Yeah, perfect. So we have 0 and 2. Okay, so we have cases. We have for x greater than or equal to 2, our function is actually x squared minus 4. That is for x greater than or equal to minus 2. Then for x, this one is actually our function, how our function is varying. That is for x greater than or equal to minus 2. Then for x in the range 0 to x, our function is 2ax plus b. Then for x, which is less than or equal to 0, our function is e to the power of x. So we don't care how the graphs looks like, but we are told that it's continuous. So we are going to use this approach. We're going to approach this 0 from the negative and approach this 0 from the positive. And same applies on this one. We are going to approach 2 from the negative and approach 2 from the positive. So those are the 2 things which we are going to do and which is going to give us solutions. So let's first start with the 0 from the negative and 0.